Hello and welcome to Tech Simplified TV. For last 6 episodes, we have discussed different topics related to VLSI Physical Design. We have already covered clock tree, partitioning, flow planning, pin assignment, power and ground routing, placement, global routing. We tried to understand the mathematical approach. Now, in the same series, it's time for detailed routing. In today's episode, we will talk about different aspects and techniques of detailed routing. If you are interested, stay tuned and focused till the end of the video. Look at the pointers we are going to discuss in today's episode. First, design flow and detailed routing. In our previous episode, we have discussed about global routing. After global routing, there comes the step of detailed routing. So today that is our point of discussion. And next is different routing techniques. Horizontal and vertical constraint, zone representation. After that, horizontal and vertical constraint graph. Channel routing by left edge algorithm. Channel routing by Dogleg routing. Next, switchbox routing. After that, over the cell or OTC routing algorithm. Next is OTC routing methodology. And finally, modern challenges in detailed routing. So today we will keep our discussion over all these points. So we are done with this slide. Let's move to the next slide. So design flow and detailed routing. This is a diagram we are using in last few episodes based on physical design, and as we can see here, after system specification, architectural design, functional design and logical design, circuit design, these things are done. And then comes the physical design, and physical design consists of all this partitioning, chip planning, placement, clock tree synthesis. We have already covered all these steps. And then comes signal routing, and even signal routing. And there are 3 sub-steps: global routing, detailed routing and specialized routing for those specialized net which require more attention. And we have already covered global routing. So today it's detailed routing. In VLSI, routing is crucial step that connects the components of a chip. So there are multiple components on a chip and they are connected to realize the intended function for which the chip is designed, and that connection is done by routing. So it involves determining the paths for electrical connection from which module to which module is connected, and these connections are implemented through metal layers. So from which metal layer the connection will be drawn. Routing is all about that. So routing is divided into 3 major steps: global, detailed and specialized routing. The layout region is represented during global routing using a coarse grid of global routing cells, G cells, or more general routing regions, channels, switch boxes. After global routing, each net undergoes detailed routing. So first is global routing, and that uses a coarse grid, and detailed routing is more specific about layers, metal layers, via, and at which layer it will get connected and all, which pin will go to which layer. So that is much more, detailed routing is much more specific about routing tracks, vias and metal layers. And the layout region is represented during global routing using a coarse grid of global routing cells or more general routing regions like channels and switch boxes. After global routing, each net undergoes detailed routing. And objective of detailed routing: assign route segments of signal nets to specific routing tracks, vias and metal layers while following global route and design rule. So global route uses coarse grid, and in detailed routing follows global routing and do more specific allocation of vias and metal layers and routing tracks, and it also follows design rule. And what are the key advantages? A detailed routing of one cell can be performed independently as long as routes remain connected across neighboring G cells. If the design is very big and complex, each G cell can be independently routed. The designer can concentrate on the smaller part, although the G cell must be connected to its neighboring G cells. And this enables an efficient divide and conquer strategy. This way small part is done, and that when the design is big and complex, that gives an edge. This approach gives an efficiency. So this enables an efficient divide and conquer strategy and supports parallel algorithm. If routing on multiple section of the design runs parallelly, actually it saves the time, allowing detailed routing runtime to theoretically scale linearly with layout size. So the runtime is linearly related with the layout size. If the layout size is big, then runtime is more. If the relationship would have been quadratic or exponential, then it would have been a little bit more complex. And traditionally, detailed routing occurs within routing regions such as channels and switch boxes. Modern designs use over-the-cell routing, allowing routing over standard cell. Over-the-cell or OTC routing we will discuss in later slide in detail. In case of modern designs, OTC routing is used. Due to technology scaling, modern detailed router must consider manufacturing rules and impact of manufacturing faults. So manufacturing faults like reliability and variability impact must be considered, and it must strictly follow the design rules, because in advanced node the error related to the lithography is much more prominent. Detailed routing must follow all these rules very strictly. We are done with this slide. We will move to the next slide. Different routing techniques: channel routing, switchbox routing, OTC or over-the-cell routing, and classical channel routing. Type of detailed routing. The first one is channel routing. Type of detailed routing where connections between terminal pins are routed within a channel with no obstacle. This is channel routing. Connections between nets are done. This is the channel and there is no obstacle and pins are on the opposite side. And the connections run from left to right, that is horizontally. Pins are located on opposite sides of the channel. Conventionally, the channel is oriented horizontally, this direction, with pins on top and bottom. In row-based layouts, routing channels typically have uniform width. In gate array and standard cell circuits with more than 3 metal layers, channel height or number of routing tracks is also uniform. Next is switchbox routing, used when pin locations are on all 4 sides of a fixed size routing region. So this is a fixed size routing region and pin connections are on the 4 different sides, not on opposite top and bottom sides. So that is switchbox routing. There is a design and these are 4 modules, how it's connected. If we want to route this area, pins are on opposite sides, here also like that. So this portion can be done by channel routing, and here in the between, when all the pin connection, all the nets are crossing each other in this zone is routed by switchbox routing. OTC or over-the-cell routing utilizes additional metal tracks, that is metal 3 and metal 4, that are not obstructed by cells, allows routes to cross over cells and channels. Only metal layers and tracks not occupied by cells can be used. When cells use only polysilicon and metal 1, routing can be performed on metal 2 and metal 3 etc. and unused metal 1 resources. So this is a channel routing situation, and this is the 3-layer OTC routing. We can see that number of connections are more here compared to this one, and here is over the cell, these connections is done over the standard cells, and here congestion is less, and metal 3-layer is used for this purpose. And classical channel routing area is rectangular grid with pin location on top and bottom boundaries. Pin are placed on vertical grid lines or columns. Channel height depends on number of tracks needed to route all nets. In 2-layer routing, 1 layer is reserved for horizontal track while other layer is reserved for vertical track. Preferred routing direction is determined by flow plan and standard cell row orientation. That is classical channel routing. So these are routing techniques. We are done with this slide and we will move to the next slide. Horizontal and vertical constraint. Horizontal constraint. A horizontal constraint between 2 nets occur when their horizontal segments overlap while being placed on same track. So we cannot place them on the same track. There is an example. This is A and this is B and this is C. So look, C and B, they are crossing each other. If we place these 2 nets on the same track, they will overlap. Although if we place A and B on the same track, or A and C, they are not overlapping each other. So we can place A and C or A and B, they are horizontally unconstrained, whereas C and B are horizontally constrained. We cannot put them in the same track. That is horizontal constraint. Try to remember this. We will use this concept in later slide. And vertical constraint. Vertical constraint, a vertical constraint between 2 nets when they have pins in the same column. Look, A and B, they are on the same column. Here B and A are not in same column, although here A and B are in the same column. So this means that the vertical segment extending from top must stop within a short distance to avoid overlapping with the vertical segment coming from bottom in the same column. So that has stopped. If each net is assigned to a single horizontal track, the horizontal segment of a net from top must be placed above that of a net from bottom in the same column. In figure, that segment A is placed on B. In figure, this constraint ensures that net A's horizontal segment is placed above net B's. To resolve this constraint, at least 3 columns are needed to separate the two nets, while a vertical constraint implies a horizontal constraint. If this situation is quite similar like this, if that is vertically constrained, that is also horizontally constrained. Although the reverse is not always true. While a vertical constraint implies a horizontal constraint, the reverse is not always true. However, both constraints must be considered when assigning segments within a channel. If there is a pair of in both the column it's vertically constrained, so in this case we have to add another net. So we are done with this slide. We will move to the next slide. Now zone representation. Zone representation in a channel, each horizontal wire segment must extend at least from the leftmost to the rightmost pin of its net. Otherwise the connection is not complete. Each horizontal wire segment, the wire segment connecting to remote pins, they must be extended at least from the leftmost to the rightmost pin of its net. So let S column or set column represent the set of nets passing through column call. This includes net either have a pin in column or connect to pins on both sides of column. Since horizontal, this is a rule. Just remember, since horizontal segments cannot overlap, each net in S column must be assigned a separate track within that column. However, not all columns are necessary to define the entire channel. So rule is, so these are the pins, and now if we draw columns like this, so A, B, C, D, E, F, G, H, I, J, K. So we are only considering these 4 because other columns are subset of either of these 4. If we consider, the rule is pin assigned to that column is either it's starting from here or connecting the, if that is set A, then the rule is that set represent the set of nets passing through column. Either it has a pin in column or it connects pin on either side of the column. So here only one pin. In B, this net is connecting on 2 sides. So these from this one pin, this pin and that pin. Although if we consider the C, we have all these 3 and more 2. So this is a bigger set. SA and SB are subset of SC. So we will consider set C, not A and B. This way, these 4 are considered. If a column I has a net set SI that is a subset of another column J, that is SI belongs to SJ, then SI can be ignored as it imposes fewer constraints on routing. In the above figure, every S column is a subset of at least one of SC, SF, SJ or SI. These columns C, F, G and I form minimal set needed as they collectively include all nets. The relative positions of net in channel routing instance defined by horizontal and vertical constraint can be represented using horizontal and vertical constraint graphs. These graphs help to estimate the minimum number of tracks needed and identify potential routing conflicts. In the next slide, we will see that how this zone representation can be expressed in terms of vertical and horizontal constraint graphs also. Now let's see what is happening here. This is connecting A to A, that is A, net A, that is net B, this is net C, this is net D and this is net E. So A, this is B, this is C, this is D, this is E. So here under this column A, B, C, D and E. And now if we consider this column F, so here this one is connecting D. D is connected, pin F is there, pin F, A, pin A is there, pin F, pin A and this D, this is net A and net F. So A and F and these on 2 side D. So this is D, 3 nets. Now SG on G, G and F and this is D on G, F and D and on I, D and that is H. So G is here, H is here and D is here, H is here and this G and G connected, so G is here. So this way zone representation is done. So we are done with this slide. We will move to the next slide. Now let's see how from zone representation we can get horizontal and vertical constraint graph. Now, horizontal constraint graph, a graphical representation can be used to depict the nets within a channel. Graph theory, it's a mathematical theory from abstract algebra, and that is extensively used in this placement routing in all these steps. So this can be done using a horizontal constraint graph. A graphical representation can be used to depict the nets within a channel. Vertical and horizontal constraint graph we have already used in our previous episodes on physical design, and in all these episodes we can see this graph theory from abstract algebra that is absolutely very necessary and extensively used in physical design. Placement, routing, in all these steps and all the tools, the EDA tools which does it, they all have these mathematical models inside it. So this can be done using a horizontal constraint graph or HCG when nodes, that is V, represent the nets in the netlist and edges exist between two nodes if their corresponding nets belong to the same set. Here in the same set, this set is A, B, C, D, E. Now let's see A, B, C, D and E. Look, A is connected to D, B, E, C. This way, B is connected to A, C, D, E. C is connected to all other four, A, B, D, E. E is connected to D, A, B, C, and D is connected to A, B, E, C. In graph, these are nodes and this is edge. Nodes here represent the net between these two nodes, and edge is present if they belong to the same column. Since these A, B, C, D, E are all these five nodes nets or nodes belong to this column, so they are interconnected. Each of them are connected to rest of 4. Now SF or set F. Set F is A, F and D. A, F and D. D is connected to F and A is connected to F and D. F is connected to A and D. That is also done. Now SG is G, F and D. Now G, F and D. This set also, they are interconnected. Each of them is connected to other two. And similarly for I, G, H and D. G, H and D. Here also, each of 3 are connected with other 2. So figure 4 shows the HCG for channel routing example in figure 3. We have repeated the figure 3 here just for reference, and the minimum number of tracks required for channel routing can be determined using either the HCG or zone representation. This minimum is given by largest S column set. So minimal columns, and we have taken only those, and this is the HCG or horizontal constraint graph of this set, of this zone representation. Now vertical constraint graph. Vertical constraint graph or VCG represents vertical constraints in channel routing. Nodes V represents nets, directed edges. E exists between nodes if one net must be placed above another. In figure 5, some edges like B to C are omitted if they can be inferred from other edges like B to E and E to C. So here we can see that in VCG or vertical constraint graph, nodes represent nets. There is directed edges exist between nodes if one net must be placed above another, like B to E. So net B is placed above net E, and net D is placed above net B, and E is placed above C, and G is placed above F, and F is placed above A, and H is separate. And here another scenario, a cycle in VCG indicates a conflict where two nets overlap in column. So with this horizontal and vertical graph, we can easily determine that which net are connected, which net. And here in vertical constraint graph, we can determine which net must be placed above which net. Which net must be placed above and which will remain below of that. The scenario is completely clear from these two graphs. This diagram is different. A cycle in VCG indicates a conflict where two nets overlap in a column. Both two nets. Meaning their horizontal segments would need to be both above and below each other. An impossible situation. This is resolved by splitting the net and adding an extra track, like A to A and B to B, and that this way that is splitted and issue is resolved. We are done with this slide. We will move to the next slide. Now channel routing with left edge algorithm. Channel routing algorithms. Channel routing aims to minimize the number of tracks needed for routing. In gate array design, where channel height is usually fixed, algorithms are developed to ensure complete or 100% routing. Left edge algorithm, an early channel routing algorithm, was developed by Hashimoto and Stevens. Their simple and widely used left edge heuristic based on VCG and zone representation efficiently maximizes track usage. The VCG determines the order in which nets are assigned to tracks, while the zone representation decides which net can share the same track. Each net uses only one horizontal segment or trunk. Obviously, we know at which order, like here, since it directed, A must be placed over E, A and D must be placed over E, and C must be placed below E net E, and similarly D and J must be placed above I, whereas I must be placed above H, and again J must be placed above G, F and B, and here B is at the lowest level, then above it F and above it G. This way, the routing, that is a vertical constraint graph. That information we can get from this vertical constraint graph, and it actually uses VCG and zone representation. The left edge algorithm works as follows. Start with topmost track. For all and assigned nets, generate the VCG and zone representation. Process nets from left to right, assigning each to the current track if it has no predecessor in the VCG or it does not conflict with previously assigned net. Once a net is assigned, remove it from the unassigned list, move to the next track and repeat the process until all nets are assigned. So one at a time we are taking. Start with the topmost track. So first track A, first track, for all unassigned nets, generate the VCG and zone representation. For all other unused nets, it's using the VCG, it's creating the VCG and zone representation. Process nets from left to right. From left to right, start processing nets. For all unassigned nets, generate the VCG. Now we have started with topmost track. So process nets from left to right and assign each of their current track. Now first A is assigned and then it has no predecessor in the VCG. If that has no predecessor, if it has no predecessor, it's a starting point. So we will start with that. We will assign it, and it does not conflict with previously assigned net. So it's the starting point A, and once the net is assigned, remove it from unassigned. It's assigned, so we are removing it from the unassigned list. Now next, with the rest of the unassigned pin, we are again doing the VCG and we will move to the next track. This way we will keep doing this. Move the next track and repeat the process until all nets are assigned. This algorithm finds a solution with the minimum number of tracks if the VCG has no cycles. Yoshimura later improved track selection by considering net length in the VCG, and Yoshimura and Co. further optimized track usage by splitting nets before constructing the VCG. That was a modification by Yoshimura and Co. So this way, this is the most early channel routing algorithm, that is left edge algorithm. So we are done with that and we will move to the next slide. To handle cycles in VCG, an L-shaped dogleg, this L-shaped dogleg can be used. Doglegs help resolve conflicts in VCG and reduce the total number of tracks. Dogleg algorithm developed in 1970s eliminates cycles and minimizes routing tracks by extending the left edge algorithm. It splits P-pin nets P greater than 2 into P-1 horizontal segments, but only in columns where the net has a pin, assuming no extra vertical tracks are available. After splitting, the algorithm follows the left edge approach with subnets represented in VCG and zone representation. So dogleg routing also use left edge algorithm. Before that, it split the net. Dogleg algorithm that is developed in 1970s eliminates cycles and minimizes routing tracks by extending left edge algorithm. It's an extension. It splits P-pin nets P greater than 2 into P-1 horizontal segment, but only in columns where the net has a pin, assuming no extra vertical tracks are available. Channel routing, this is a channel routing problem. Like it's a vertically constrained from A to B is just opposite vertically coming from lower column. So it's a vertically constrained situation, channel routing issue, and now VCG without net splitting, like C is at the bottom, net B must be above it and net A must be above it, this way. Now channel routing solution is like that. A is connected, now B must be connected like this and C like that. And now look how many tracks are used. And now net splitting, it's splitting the net B, it splits P pin nets when P is greater than 2 into P minus 1 horizontal segments. Like here, B net are P greater than 2, 3. 3 nets of B are represent. So 3 is greater than 2 and 3 P minus 1, 3 minus 1, that is 2. It will split the net into 2 horizontal segment. So it has splitted like this way, B1 and B2, these two. A is connected like that, C is connected like that, and in case of B, it's B1B is connected to through B1 and this split, and now it's a little bit vertically shifted. And this, look, this one compared to this one is much more clearer. Channel routing solution. Now VCG without net splitting, that should be with net splitting. So A to B1 must be below A and B2 must be above C. So it's splitted like that only. So A to, it was directly A to B and C, and here it's like A to B1 and now B1 to C. This B is splitted into 2. So these 3 nets are connected like that. So that is channel routing solution by Dogleg routing, and here is the Dogleg, this structure. So this is Dogleg algorithm. We are done with this slide. We will move to the next slide. Now Switchbox routing. Switchbox routing algorithms are often derived from channel routing techniques. Look extended a greedy channel router by Rivest and Fiducia to develop a switchbox routing algorithm with key improvements like pin assignments are made on all 4 sides. A horizontal track is assigned automatically to a pin on the left. Jogs are used for top and bottom pins for horizontal tracks connected to the rightmost pin. And while this algorithm performs similarly to the greedy channel router, it does not guarantee full routability due to fixed switchbox dimension. Switchbox dimension is fixed. Austerhoff et al. Introduced a channel and switchbox router that consider obstacles like pre-routed nets. Kohun and Heck developed Beaver, which optimizes routing area and via usage. And Beaver offers flexibility in layer routing and employs 4 strategies: corner routing, line sweep routing, thread routing, and layer assignment. Switchbox routing has gone through a many improvisation. So Beaver offers flexibility in layer routing and employs 4 strategies: corner routing, line sweep routing, thread routing, and layer assignments. Corner routing uses horizontal and vertical segments forming bends. Line sweep routing handles simple connections and straight segments. Thread routing supports various connection types, and layer assignment optimizes layer usage. All 4 sides, here it's mentioned pins like 0, D, F, H, E, C, C, and here 0, G, F. So this connection is a little bit more complicated, and we have seen in one of our previous slide that switchbox is done where from different modules or different components the connections are coming and they are meeting a place. This zone where pin connections are coming from all sides, this complicated portion that is routed by switchbox routing. So look, D is like this, routed like this. G is a little bit complex here. G is like that, F is like that. So top, bottom, left and right pin connections are mentioned. This is the initial and this is the final scenario, how it should connect it. Corner routing uses horizontal and vertical segments forming bends. In this corner routing, these bends are here. Line sweep routing handles simple connection and straight segments. That is done by line sweep routing. Thread routing supports various connections types. It's a multi-type connections are connected by this thread routing. And layer assignment optimizes layer usage. How many layers should be used? That is using 4 different strategies do the routing, and that offers a flexibility. Now, Beaver surpasses previous academic routers in routing area and via efficiency. Another notable switchbox router, Packer, developed by Geres and Herman in 1989, follows 3 main steps: routing each net independently without considering capacity constraint, and resolving conflict using connectivity, preserving local transformation, and modifying net segments locally to reduce congestion. Packer was developed by Geres and Herman in 1989 and that has three main steps like routing each net independently without considering any other capacity constraint, and resolving conflict using connectivity, preserving local transformation, and modifying net segments locally to reduce the congestion. And Beaver is much more better than that for switchbox routing. In case of switchbox routing, Beaver performs better and much more flexible also. So these are all academic routers done in purpose of academic use it. So we are done with this slide and we will move to the next slide. Over the cell routing algorithms. Most routing algorithms focus on two-layer routing. However, modern standard cell designs use multiple layers requiring extensions to this algorithm. One common approach places cells back-to-back or without routing channels. Internal routing primarily use poly and metal 1. So above poly layer, there is metal 1 layer, then metal 2, metal 3. While higher metal layers like metal 2 and metal 3 remain unobstructed and are used for over-the-cell routing. These layers are represented by coarse routing grid of G-cell. Nets are first globally routed as Steiner trees and then detail routed. Mostly internal routing primary uses the poly and metal layers, so metal 2 and metal 3 layers. These are unobstructed and that is used in OTC. Nets are first globally routed as Steiner trees and then detail routed. Another approach introduces channels between cells, but routing within them is limited to internal layers like poly and metal 1. Higher metal layers, metal 2 and metal 3 handle most routing, making traditional routing channels unnecessary. Instead, routing occurs across the entire chip rather than in defined channels or switchboxes. OTC routing often coexists with channel routing. For example, IP block may block routing on lower metal layers, forming channels or switchboxes between them. FPGA fabrics use fewer metal layers to reduce cost, clustering interconnects into channels. FPGA also include pre-designed components like multipliers and DSP block that rely on OTC routing. Modern FPGA feature express wires on higher metal layer that cross logic elements. So OTC routing that exists with channel routing also, and in poly and metal 1, these layers are mostly used, and above layers metal 2, metal 3 are unobstructed. So OTC actually use those metal layers. This is over the cell or OTC routing algorithm. We are done with this slide. We will move to the next slide. OTC routing methodology. OTC routing follow 3 steps. Select nets to be routed outside the channel. Route these nets in the OTC area. Route the remaining nets within the channel. Several advanced OTC routing algorithms have been developed. Chameleon OTC router by Brown et al. Generates net topologies using 2 or 3 metal layers to minimize routing area. Assigns net segment to tracks. Consider technology parameter per layer such as wire width and spacing. Pong, Wong and Liu's approach, that's another approach, initially routes all nets in 2 layers, then map them onto 3 layers, uses shortest path and planar routing algorithm to minimize wiring area, assumes HVH model, that is horizontal track in layer 1 and 3, vertical track in layer 2 can be extended to 4 layer routing. That's another approach. Ho et al.'s heuristic based method, that is greedy approach with iterative heuristics, successfully solved difficult example using 19 track on 2 layers matching the optimal zone representation. And Weiser by Holmes, Sherwani and Saravzadeh uses free pin positions and cell areas to increase OTC routing capacity, selects net strategically for OTC routing. So these are 4 approaches. Now these are the OTC over the cell connections, and these feed-through passes are present. We have mentioned that in global routing in standard cell or standard cell design, these are feed-through passes. Number of pins are increasing, number of connections are more than using OTC. We can make this channel uncongested. So that is methodology of OTC routing, and we are done with this slide. We will move to the next slide. Modern challenges in detailed routing. Technology scaling and wire widths. Demand for low cost, high performance and low power ICs has driven technology scaling since the 1960s. Different metal layers use wire and varying widths, with wider wires on higher layers, improving signal speed but reducing routing tracks. Thicker wires are commonly used for clock, power supply and global interconnect. Now, routing complexity and layer configuration. Modern ICs use different metal layers configuration to optimize performance via connecting wires of different width block routing resources on layers with smaller pitches. Since wider wires are on higher layers used, that improves actually signal speed, although track for routing that is reduced, and thicker wires are used for clock, power supply and global interconnects. Now, manufacturing yield and detailed routing. Yield concerns require VR doubling and non-tree routing for redundancy. At advanced node, design rule become restrictive and specifying minimum spacing between wires and vias based on width and corner proximity. Forbidden pitch rules prohibit certain wire spacing while allowing others. So the conditions become more stringent. And via defects and mitigation. Vias connect wires between metal layers but may misalign or degrade due to electromigration. Partial via failure increases resistance, leading to timing violation. Complete failure disconnects nets. Double vias improve reliability but require additional area and adherence to design rules. Congested areas may limit via doubling options. So there are solutions, although since space is a concern, that thing can be limited by area also. Available area. Now, interconnect defects and redundancy measures. Shorts and open, that could be a possibility. Shorts or unintended wire connections are mitigated by increased spacing. These are interconnect defects that can happen during fabrication. In some other episode, we will discuss about these shorts and open things. These are very common errors come while fabrication, and this could be reason of IC failure. Shorts are mitigated by increasing spacing, though in excessive spacing raises wire length. Open are addressed via non-tree routing and redundant wiring, which improves reliability but increases short risk. So there are pros and cons we have to balance and optimize. Antenna-induced defect. Excessive charge buildup during plasma etching can damage transistor gates. Mitigation involves controlling metal to gate area ratios and rerouting via new or relocated vias. Manufacturability, aware routing, yield optimized detailed routing is proposed, but its benefits are hard to quantify pre-manufacturing, limiting industry adoption. So there are so many challenges already present, and since the device dimension reducing and because of excessive scaling and small dimension of devices and allied fabrication related reliability issues, the detailed routing become more complex and tough to achieve good result. We are done with this slide, and now this is an example. So in 130 nanometer, look how many layers are there. M1, M2, M3, M4, M5, M6. Now 90 nanometer, number of layers increasing, number of in 65 nanometer more, 45 nanometer more, and 32 nanometer. So layer stacks are shown. So number of layers are increasing as the scaling has been done from 130 nanometer to 32 nanometer. Number of layers increasing. As an example, it has been shown here. So we are done with this slide, and we are done with our today's discussion. So that is all we had about detailed routing. Here we have discussed different aspects of detailed routing. After global routing, the next step is detailed routing. We have completed it today. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any dislike, please put it as a comment. If you have a question or query, also put it as a comment. Thank you and bye for today.